Hi, I am Xiao Chuan. This is my ID, this is my course, and this is my title, Integration by Parts. Before we get into integration by parts, we will introduce integration first. Integration is also known as antiderivative. Integration is defined as infinite sum of rectangle of infinite width. When we are calculating, we may see two types of integral, that is definite integral and indefinite integral. Now, we are up to the history. So how the history of integration developed? Firstly, Exercise invented first capable of determining integral, and that is called method of exhaustion. That's when area and volume was known. Then in the 3rd century, Archimedes further developed to calculate area of parabola and approximate the circle's area. In the 5th century, Zhu Chongzhi and Zhu Geng used this method to find volume of sphere. At the 16th century, Cavalieri and Fermat computing the integral up to x power of 9 by using Cavalli's method of indivisible. In the 17th century, Barrault and Toleranczi gave the first hint of connection in integration and differentiation. Advanced integral is developed in 17th century by Newton and Leibniz that discovered the fundamental theorem of calculus that showed the connection of differentiation and integration. Bishop Berkeley applied vanishing increment that was used by Newton, and that was called the ghost of department quantities. Then Riemann formalized the integration by using limits. The most common for now is based on the real number system that Riemann's and Leibniz. Now Goldfield adapted the integration symbol at 1675, the big S. Here's a type of integral. The most common one we use are Riemann's and Lebesgue integral. So you can see that. Okay, now we are getting into integration by parts. Integration by parts was invented by Brooke Taylor. It is used to transfer a product function into a function that can be easily solved. Before we get into the question, we need to know how it came from. The form of integration by parts formula. So we know that this integration by parts is used to calculate the product function. Product function is like this. And firstly, we must differentiate the product rule. So then we will get this. We differentiate fx gx, we will get f prime x gx and plus fx g prime x. Then we add the indefinite integral to all of them, rearranging this one to here and this one to here, and we will get this. Then we get an integration by parts formula. So to make it easier to remember, we will let fx equal to u, gx equal to v, f prime x equal to du, g prime x equal to dv. So in this, we use the substitution method and it became this. And it is much more easier to remember. Now, we're heading into the type of question. The first type of question is x e power of x dx. Firstly, when we let something to be u, it must be differentiated. And we let something equal to dv, it must be integrated. So we let u equal to x. Why we let u equal to x? We let u equal to x because it can be differentiated repeatedly until it becomes 0. why we let dv equal to ex, e of the power of x dx, is because we can let e power of x dx because it can be integrated repeatedly without difficulty. Then after we differentiate u, we get du, and we differentiate x, we will get dx. And we integrate e of the power of x dx, we will get e of the power of x. And by using the integration by parts formula, this is, we will get that's like u du, we applied it inside, u dv, we applied it inside, equal to u v minus v du. Just put it in, or just put it in together. Then we will get this kind of thing, and this we will just use normal integration, then we will get this. And remember to plus a c, and c is a constant. So up to the second question. The second question is integrate e power of x cos x. We can either put e of the power of x equal to u, or cos x equal to u, or e of the power of x equal to dv, or cos x equal to dv. This is because they can be integrate and differentiate with no difficulty. We can let u and dv either e of power of x or cosine x. So I will let u equal to power of x and dv equal to cosine x. Then we will get du equal to e power of x and v equal to minus sine x. Then we use the integration by parts formula. We just throw it in, or we just throw it in. Then we will get something like this. Then in here we will get another product function. So when we get another product function, we use integration by parts to do it. So we can let either one equal to u or either one equal to dv, but I will let u equal to dx because it seems much easier. So I will let u equal to ex and dv equal to sine x. So when we differentiate u equal to ex, we will get du equal to ex. And when we integrate dv equal to sine x, we will get v equal to cosine x. And by applying the integration by parts formula, we get something like from here to here. Okay, so from here to here we applied it. So we can see this thing and this thing are the same. So because they are the same, we let this equal to I because they are the same. Then we will take this to put it here, and at the end we divide it, and then we take the I become its original form. Then this will be the answer. Here, no more. Now, the third question is ln x divided by x to the power of 5. We will integrate this. Because ln x cannot be integrated, so we will take u equal to ln x and dv equal to 1 over x power of 5. So after we differentiate ln x, we will get dx 1 over x dx. And when we integrate dv equal to 1 over x power of 5, we will get minus 4 over x power of 4. Then we apply the integration by parts formula. We will get this. Then we will use the norm. Then we will just fix it and fix it, and we just use the normal integration. Then the answer will come out. So we're up to this question. So this question, just like I said, we cannot integrate ln, just all the ln, we just can't integrate it. So we will let u equal to ln x plus x squared, and we will let dv equal to dx. So when we integrate, we differentiate u equal to ln x plus x power of 2, we will get this, and we integrate this, we will get this. So we just apply the integration by parts formula, you'll get something like this. And we just make this simpler, then we must take out the x here. And when we take out the x, we must cross out the x. And because we can't integrate this, we can't integrate this, so we plus a 1 here and minus a 1, that will come back here. Then this, we will just put it like this, and the minus 1 here is another one. So when this one, we can cancel out this, then you will get this, then you can integrate easy to get this. And then when you get this, we can also integrate it by using the formula, something like this, by using this formula. It's all the same. This is x, this is x prime. So sometimes integration by parts will not succeed. For example, it will lead you to more complicated integral than the original one. So the first question is x the power of square sine x dx. So when we let, so at first we must, in the correct way of doing, we will let u equal to x squared, because it can differentiate repeatedly until it becomes 0, and we will let x sin x equal to dv, because it can integrate repeatedly without difficulty. But if we do it wrongly, just take u equal to sin x, and we take dv equal to x squared, it will come out a more complicated thing. And we apply the integration by parts formula, we will get this kind of function, and you can see this is much more complicated, and it is not getting easier to solve, it's getting more complicated. So when it gets more complicated, it will not succeed. The second type of question that will not succeed is when the original integration was laid back, such as this, and we will let u equal to x, dv equal to 1 over x squared. Then we will get du equal to dx and v equal to negative 1 over x. By applying the integration by parts formula, we will get this and this. This is u v u minus v du. Okay, then after we will get, then at the end we will get this. It is the same. So this and this are the same, and this is considered C. So until the end we will get the same original integral and it fails. So sometimes we cannot, sometimes integration by parts will not succeed. So the last thing I'm going to talk about the tabular integration. Tabular integration is used when f(x) can be differentiated repeatedly becomes 0 and gx can be integrated repeatedly with no difficulty, or get it back, gx. It will make the work easier and it is a natural candidate for integration by parts. So example of tabular integration. We take back the question number 1 as integrate x ex e of the power of x dx. So we will let f(x) x equal to x and gx equal to e of the power of x. So we differentiate this. We differentiate x and we differentiate repeatedly until it becomes 0, and we integrate gx until the differentiate becomes 0, and we will stop there. So after we differentiate and integrate it, we'll draw a line that is from here is 1, here is 2, here is 3, here is 1, here is 2, here is 3. The arrow of 1 will get to 2, the arrow of 2 will get to 3, the arrow of 3 will get to 4, the arrow of 4 will get to 5. And it will just like, the first one is sure positive, the second one is sure negative, the third one is sure positive, the fourth one is sure negative, and it repeatedly doing that. And the first one is a negative, we just throw it in. First, we throw it in equal to x, positive x ex minus e of the power of x times 1. And then there's no more, plus c. C is a constant. And the last thing is, how does integration used in our daily life? We use integration mostly in finding areas. For example, you split the soup on the floor. You want to find the area of soup, you can use integration. Firstly, you break up the non-geometric shape and form it into many tiny geometric shapes. Then you calculate all the area of the tiny geometric, and we can get the approximate area of the soup. So this is how we apply integration in our daily life. Then that's the end. Crying. Goodbye.